So this is our AP Chemistry lesson video for Chapter 6. It's Part 2, and I'm going to cover 6.3, 6.4, and 6.5. So first thing we're going to start with is talking about Bohr's model and emission spectra, kind of how they're related. Because we're kind of just talking about, this is kind of where we go into a little bit of the physics side of chemistry. Because of course, the higher you go into chemistry, you'll learn that chemistry, physics, and calculus just all merge into one at that point. So a spectrum is produced when radiation from a source is separated into its different wavelengths. So if we take white light and pass it through a prism, we'll see all the colors of the rainbow. Spectrums from light containing all wavelengths is called a continuous spectrum. So this would be a continuous spectrum. Notice I don't see any black areas. A spectrum containing radiation of only specific wavelengths is called a line spectrum. So this is what you see when you look at a specific element and the light it's emitting. Okay, if you remember in honors, I showed y'all where we would plug the tubes in and I would turn the electricity on and you'd see the different colors. You also saw the flames test. So if you look through something called a diffraction grating, you will see just the specific lines which go with specific wavelengths of light, which of course the light's coming from the electrons falling from excited states. So the Rydberg equation was used to calculate the line spectrum wavelengths for hydrogen. Now don't worry, I'm just showing you this. We're not going to use this formula. Okay, a lot of times some of the sections of the book are kind of background information to get us to what we really need to know for chemistry and for the AP exam. Okay, so we're not actually going to use this, but it's just talking about like your N1 and N2, those are our energy levels, and we're trying to figure out wavelength based on those energy levels. Alright, so Bohr based his model on 3 postulates. First part is only orbits of certain radii or definite energy are permitted for the electron. So for example, it can be on energy level 1 or 2. It can't be in between. Number 2, an electron in an orbit has a specific energy and will not spiral into the nucleus. Okay, so once it's on energy level 1, it's not just going to slowly spiral into the nucleus because we know a negative and a positive are attracted to one another. Okay, so that's not going to happen. And then number 3, he said energy emitted or absorbed by the electron can only change in multiples of h nu. We talked about that in our last video. So as long as it gains a quantum, it can jump. If it gains less than a quantum, then it's not going to be able to jump. So Bohr calculated the specific energy levels using this equation. So if you notice, this equation was based on the one we saw earlier, but we're still not going to use this one. Okay, so his involves things you've seen like energy, Planck's constant, speed of light. It still has that Rydberg constant from the previous one. And when you see n, it's just referring to energy level, just whenever you see n, because that's what n is in quantum numbers also. So the energies of an electron of the hydrogen atom are negative for all values of n. So every energy level that the electron is on has a negative energy associated with it. So the more negative the energy is, the more stable the atom is. So y'all, that's one thing that just is a common thread throughout all of chemistry, is you want the lowest energy possible. That's the most stable. So you either want it the closest to 0, or if possible, you want it the most negative. Because releasing energy or having low energy is always more stable than having a buildup of energy. The energy is most negative for n equals 1, which makes sense because the electron is the closest to the nucleus. So you got to remember, y'all, an electron which is negative is attracted to a positive nucleus. So it wants to be as close as possible. As n gets larger, the energy becomes less negative, but it's still negative. Because remember, it's negative for all values of n. So the lowest energy state, which is n equals 1, see how n equals 1 just means the first energy level, is called the ground state of the atom. When the electron is in a higher energy level, the atom is said to be in an excited state. Now y'all, this is for hydrogen only. Ground state for every electron is not necessarily the first energy level, but since hydrogen only has one electron, its one electron resides in the first energy level. So if it's in energy level 1, that's ground state. If it jumps up, it's excited. But for like example, lithium, it has 2 electrons in the first energy level and 1 in the second. So like lithium would look like this because it has 3 electrons total. The third electron cannot go into the first energy level. That's not possible. So for the third electron, the second energy level is ground state. So do you see the difference? This is factual for hydrogen only. For other elements, ground state in general is just the lowest energy level for that electron. So if all other energy levels are full, it's the lowest one that electron can get into. So when n equals infinity, so as we're just moving farther and farther and farther away from the nucleus, the energy approaches 0. Thus, the electron is removed from the nucleus of the hydrogen atom. So as we go up in energy levels, from 1 to 2 to 3 to 4 to 5 to 6 to 7, and we keep going, eventually the electron gets so far from the nucleus that it will be gained by another atom that happens to be in the same vicinity. Okay, because at that point they just got so far that the attraction was too little to hold the electron. So electrons change energy levels. We discussed this in honors. So energy must be absorbed for an electron to move to a higher energy level. Radiant energy is emitted when the electron jumps to a lower energy level. So y'all, the important thing is energy is emitted when it falls down. So like if it asks you about when do you see light, or when is that line spectrum going to happen, it's when it falls down. Okay, so we already know these two formulas. E equals h nu, Planck's constant, times frequency. C equals lambda nu. So if you kind of combine them, then you get E equals, you see how if we solve for frequency here, it would be C over lambda. Here, let me write it just to make sure you know what I'm talking about. You see how it'd be C over lambda? Well, if nu equals C over lambda, what I can do is just plug that in for nu. So we get E equals H times C, those are both constants, over wavelength. So what that means is as your wavelength increases, your energy decreases, since wavelength is in the denominator. Alright, so it says, using figure 6.14 in your book, which is on page 220, now this is the old book, so I don't know actually what page it's on in your new book. Predict which of the following electronic transitions produces the spectral line having the longest wavelength. Okay, so y'all, if you look, we said E equals hc over wavelength, over lambda. So wavelength increases as energy decreases. So the picture in your book just shows the energy differences between all of the levels, your different energy levels. So what you would want to do is pick the two energy levels that are closest together. But the reason that I can answer this without even looking in the book at the figure is I know as you get farther from the nucleus, the energy levels get closer. So here we're going from 2 to 1. Those are close to the nucleus. Here we're going from 3 to 2. Those are a little bit further, so those will be a little closer together. Here we're going from 4 to 3. Those are further from the nucleus, so they're even closer together. So since there's less of an energy difference here, we're going to have a longer wavelength. So since E equals hc over lambda, the higher the wavelength, the lower the energy change. And N4 to N3 would have the longest wavelength because as you get farther from the nucleus, energy levels get closer together. The closer the energy levels, the smaller the energy difference. The smaller the energy difference, the larger the wavelength. It's just mathy stuff. You know, math. So you try this one real quick. I'll assume you've already done that, and I will do it now. So it says, indicate whether each of the following electronic transitions emits energy or requires the absorption of energy. So yeah, if we're going farther from the nucleus, up in energy, we need to absorb energy. If we're falling closer to the nucleus, we can release energy. So this says from 3 to 1. So that's falling towards the nucleus, so it is going to emit energy or release energy. Here we're going from 2 to 4. We're jumping up, so we would need to absorb energy. Okay, so it's just all about how far you are from the nucleus. All right, so limitations to Bohr's model. So remember, Bohr's model was incredibly accurate for hydrogen. So the problem is every other element is not hydrogen. So Bohr's model can only explain the line spectrum of hydrogen, not the other elements. So then you may wonder, well, why do we still talk about him? Well, we did get some important ideas from Bohr's model, and that is that electrons exist in energy levels. Okay, we still use energy levels today, and energy is involved when electrons jump to different energy levels. So, moving on to 6.4, the wave behavior of matter. So we just talked about how light sometimes acts like a wave and acts like a particle, but now we're saying matter, which has actual mass and takes up space, has a wave behavior. So what is going on here? So de Broglie suggested that as the electron moves around the nucleus, it is associated with a particular wavelength. Okay, so think of it kind of like this. Like as it's kind of working its way around its energy level, it's kind of acting like a wave as it goes. Now, of course, this is a simplified version. We know it doesn't just orbit the nucleus like this. But that's a simplified version, so we can get an idea. So when it's traveling, it's kind of like it's traveling in a wave behavior. But an electron is an actual particle. So de Broglie used the term matter waves to describe the wave characteristics of material particles. He proposed that the wavelength of any particle depends on its mass and velocity. So here we have some variables that you're familiar with. Lambda is just wavelength in meters. H is still just Planck's constant, which is 6.626 times 10 to the negative 34 joules times second. Here N is mass and V is velocity. Okay, so this is not a nu, this is not frequency, this is just a V. So V is velocity. Based on his formula, the wavelength of an object of normal size would be so tiny it cannot be observed. So what that means is because an electron is so small, its wavelength can actually be noticed if you could see it. But an object of normal size, so like if I threw a baseball, because that baseball is a normal size object, the wavelength would not be able to be recognized. All right, so that's what his formula is saying here. Because mass is on bottom, so of course as mass increases, what happens to wavelength? It decreases, so you're just not going to be able to notice it. All right, so let's look at this one real quick. So it says, what is the wavelength? Let me open my marker. That would help. What is the wavelength of an electron moving with a speed of 5.97 times 10 to the 6 meters per second? So that's my velocity. Sorry, my lambda looked kind of weird right there. The mass of an electron is 9.11 times 10 to the negative 31 kilograms. So there's my mass. All right, so we're looking for wavelength. We have velocity. We have mass. Okay, so remember, my formula is wavelength equals h over m times v. So we have h all the time. That's just Planck's constant, 6.626 times 10 to the negative 34 joules times seconds. All right, so we have our mass. It's 9.11 times 10 to the negative 31 kilograms. And kilograms is correct for mass for this type of problem. All right, and then we have our velocity. It's 5.97 times 10 to the 6 meters per second. All right, so when you do a problem like this, the math should hopefully be super easy. You shouldn't have any trouble with the math. Like to do the math, you should get 1.22 times 10 to the negative 10. We'll hold off on the unit for just a second. All right, so it's the units that can throw you off. So one thing you may not know is a joule is just a kilogram times meters squared per second squared. Okay, so it's a kilogram times a meter squared per a second squared. So kilograms will cancel. One of the meters will cancel. And then here is a second that's on top. This is a per second. So one of our seconds will cancel. This is a second in the denominator, but this is a second in the denominator of the denominator. So that really flips it back to the numerator. So that other second cancels. So that's how we get our unit of meters. Okay, y'all, otherwise, if units are scary, although they shouldn't be, they help you get stuff right. But if that was kind of scary, you know the unit for wavelength needs to be meters. Okay, we already discussed that. So if you couldn't figure out how to cancel your units, but see, canceling units helps because then you know for sure you did your math right. You know, if you can't get the correct unit, then something might be wrong. Okay, so the important thing to remember for this is mass is supposed to be in kilograms because of the fact that a joule is based on kilograms. All right, so you pause it, try this one, and then we'll look at it together. So it says calculate the velocity, so this time I'm looking for a V, of a neutron whose de Broglie wavelength is 500 picometers. So here's my wavelength. The mass of a neutron is 1.67 times 10 to the negative 27 kilograms. So here is my mass. All right, got a lot of things happening here. All right, so let's start with our original formula. So our original formula is wavelength is h over mv. We are trying to solve for velocity. So remember, y'all, when you are solving for something in the denominator, first thing you need to do is get it to the numerator. Okay, so I'm going to multiply both sides by velocity. So see, velocity times wavelength is h over m. But I'm trying to get velocity by itself. So then I can divide both sides by wavelength. So velocity is h over m times wavelength. All right, so I got my formula. The problem is, though, what did they give me wavelength in? Picometers. Wavelength has to be in meters. Okay, so I start with my 500 picometers. 1 picometer, you can use your SI prefixes chart, is 10 to the negative 12 meters. All right, so once I multiply that, I get 5 times 10 to the negative 10 meters. Okay, so now I have a correct unit for wavelength. I have a mass, and I always have h. So now I'm ready to plug in. So h is 6.626 times 10 to the negative 34 joules times seconds. My mass is 1.67 times 10 to the negative 27. And they conveniently gave it to me in the correct unit of kilograms. And my wavelength is 5 times 10 to the negative 10 meters. All right, so again, the math is easy. All right, once you plug that in, you should get 793.53. But now let's look at these units. Okay, so remember, joules is kilograms times meters squared per second squared. Okay, so I can see my kilograms is going to cancel. Here's a second on top, here's a second on bottom, so one of my seconds will cancel. Look. All right, we got a meter on top and a meter on bottom, so one of my meters will cancel. So if you look, I'm left with meters per second. Is that a unit for speed or velocity? Yes, it is. So there we go. That's all you had to do. Okay, like I said, it's the units that kind of throw people off sometimes on this one. But y'all, the better you understand units, the better you actually understand the science behind it. Like if you don't understand the units, you just kind of memorize stuff. All right, so a few years after de Broglie published his theory, it was found that electrons, like X-rays, will diffract when passed through a crystal. Diffraction is normally associated with waves. So again, we're discovering that light kind of behaves like a particle, kind of behaves like a wave, but we're understanding that actual particles sometimes behave like waves too. So diffraction is when something bends through an opening or around a barrier. So they're finding that electrons, which are actual particles, will diffract or bend when they pass through a crystal. Okay, and so again, that's a wave behavior, but yet a particle is doing it. So Heisenberg's uncertainty principle states that when an object has an extremely small mass, like an electron, it is impossible for us to simultaneously know both the exact momentum is based on mass and velocity, and location. So in other words, we cannot know the exact speed and location. If an object is normal sized, then the uncertainty would be too small to matter. So, last section for this video, quantum mechanics and atomic orbitals. So the Bohr model assumes that the electron is in a circular orbit of a particular radius. So remember, he's kind of putting it like a solar system. We now know, or hopefully you remember from Honors Chem, that the orbitals and energy levels and sublevels, they all have very odd shapes. So in the quantum mechanical model, the electron's location is based on the probability that the electron will be in a certain region of space. So that's where we start getting those weird shapes that we'll see. So quantum numbers. Now in honors, we only focused on n. Technically, technically in AP we only have to focus on N, but I'm going to go ahead and teach you all 4 because I don't know what you're going to do after this class. You could end up in chemistry in college and they might want you to know all of them. So we're going to go over all of them real quick. So N is the principal quantum number. That lets me know the energy level. Since there's 7 rows on the periodic table, N can be 1 through 7. L is the angular momentum quantum number. That lets me know what sublevel it is. So when we're talking about sublevel, S is 0, P is 1, D is 2, and F is 3. M sub L is the magnetic quantum number. Sometimes this will just be called M. And it represents the orbitals. So y'all, when you're doing orbitals, S has 1 orbital. You set it up like a number line and put 0 in the middle. So its number would be 0. P has 3 orbitals. So I'll put 0 in the middle. I'm going to go negative to the left, negative 1, and then positive to the right, 1. And then D has 5. So I would set 0 in the middle, negative 1, negative 2, 1, 2. And then F has 7. So I'll put 0 in the middle, negative 1, negative 2, negative 3, 1, 2, 3. So that's why I put these are your options. And then the spin magnetic quantum number, M sub S, or sometimes they'll just call it S. So sometimes books will call this M and then S, or you'll see M sub L, M sub S. That's the spin. If, you know how we fill in the electrons like this, if the arrow is up, we call it positive 1/2. If it's pointing down, we call it negative 1/2. So that's what all the quantum numbers actually mean. So again, we will mainly focus on N though, and that's just the principal energy level. So if N's 2, I know I'm on the 2nd row of the periodic table. So it says, predict the number of subshells in the 4th shell, N equals 4. Give the label for each of these subshells. How many orbitals are in each of these subshells? All right, so we have N equals 4, so that's the 4th energy level. So let's think about what has a 4. I know there's a 4s, I know there's a 4p, I know there's a 4d, and I know there's a 4f. So that means 4 sublevels total. Y'all, the principal energy level tells you how many sublevels. So N equals 1 has 1 sublevel, 1s. N equals 2 has 2, 2s, 2p, like that. All right, so N equals 4 has 4. It's 4s, 4p, 4d, 4f. Then it says how many orbitals in each of these. Well, we all know S has 1 orbital. P has 3 orbitals, D has 5 orbitals, and F has 7 orbitals. Okay, y'all remember that from electron configuration. See, that's where we're headed. And y'all know y'all thought electron configuration was easy. We just had to get past all this background information to get to it. Okay, so there's what I just said. So y'all try this one. Okay, pause it, and we'll come back and try it together. So I'll assume you've done that already. All right, so it says, what is the designation for the subshell with N equals 5 and L equals 1? Okay, so remember, N equals 5 means it's going to start with a 5. So it's either going to be 5s, 5p, 5d, 5f. But then it says L equals 1. So when L equals 0, that is S. If L equals 1, that's P. If it's 2, that's D. If it's 3, that's F. So once it tells me L equals 1, I know that it's 5p. It says how many orbitals are in the subshell. You already know that. P has 3 orbitals. Then it says indicate the values of ML for each of these orbitals. So that's where this comes into play with the number line. Okay, you know 5p has 3 orbitals, so we put a 0 in the middle, -1, and +1. All right. And so like I said, the only part of the quantum numbers that may be confusing to you are the L, M, and S ones. But like I said, the AP exam should only focus on N, which is, of course, your principal quantum, which is pointing out the energy level overall. All right? And so there's our answers. Well, and we're done with part 2. So hopefully this isn't too bad so far. We got past all that like background information with all that wavelength and all that stuff. And so we'll get to electron configuration. It's coming.